Hi, geology students. I believe this is the last slide that we left on, and we were talking about the Richter scale. And there is another scale that measures the energy of an earthquake. And what they did was the seismograph obviously measures the ground motion in one instant, but a really big earthquake is going to last minutes. It's going to release energy over hundreds of kilometers along a fault zone. So we need to sum up, the energy for the entire record. So what happened was there's this other, so the Richter scale was essentially modified. It doesn't replace it, but it adds one magnitude to to all 8+ earthquakes. So now if you have like something that's an 8+, it'll be above a 9. So in Alaska in 1964 there was an 8.4 on the Richter scale. So now it's 9.2 with this new scale that's used. So this is a really neat kind of curve and charts that show a bunch of different things. But first, what I want to show you guys over here is this is the magnitude. I believe this is on the Richter scale over here, and this is the number of earthquakes per year worldwide. And this is neat because over here, this is the energy equivalence, and this would be the earthquakes. And down over here, you have basically a modern lightning bolt. And that would be like, would be about a 3 here. And then here you have a Hiroshima atomic bomb. And this is roughly about 6.5. And then you have the world's large nuclear test, which it looks like about a little bit above an 8. But this is kind of a nice little graph to make some comparisons. But up here, it says basically here, this is magnitude. So again, your magnitude is your Richter scale, and then versus your ground motion and energy. So if you have, like, for instance, if you have a magnitude change of 1, your ground motion change is going to be 10 times that, and your energy change is going to be about 32 times that. So for each magnitude, the number on the scale increases energy released by 32 and amplitude of the surface wave by 10 times. So remember, amplitude is the height of the wave. So this is kind of a nice comparison, comparing magnitude versus ground motion. So here's just another chart, average number of earthquakes of various magnitudes per year worldwide. Less than 2.5, typically not felt but recorded. And you have ones that are greater than 8. And these occur basically 1 every 5 years. And here's just for instance here, major earthquakes, serious damage result between 7 to 7.9, and the average number per year is 20. So this is kind of interesting. This is kind of the forecasting earthquakes, and there've been some recurrent studies that have been done in California. Obviously, this is where most of our earthquakes occur, is in the U.S. And it's just showing you here are the historical records and paleoseismic studies for the last 1,400 years. So they can average stuff out. They can do some statistics to see what's going on in probabilities. And it looks like here that the lowest probability is going to be this right here, North Coast, less than 10%. But basically the highest probability is Parkfield, which is like 90% here. And Imperial, California is at about 50% here. So this is the San Andreas fault that runs through here. So what type of fault is the San Andreas, guys? It is a strike slip fault. It's not a reverse fault or a normal fault. Do you guys remember what happens when you have a normal fault? A normal fault, what happens is it forms an extension. So if you pull apart or put extensional stress on a rock, what's going to happen is it's going to go like this. So can you see? So it's going to go down like that. And when you compress rocks together, the hanging wall is going to move up relative to the foot wall. So remember the little miner? I talked about the miner that has his head on the footwall, or he has his head on the hanging wall and his feet kind of dangle on the footwall. So you have the hanging wall and then the footwall, and the hanging wall is where his head is, and his footwall is where his feet dangle. And that's kind of, they use that miner as a reference point or a reference frame. So when the rocks are squeezed or they're pulled apart, then they can see which way the rocks are moving. Are they being, if you squeeze something, they're going up, and then if you pull something apart, they're going to go down like that. So but this one over here, this is the strike slip fault is one that moves like this. It moves horizontal like this. So it's not moving vertical. There's no vertical component. This one is just horizontal like this. So here's kind of this is a map of the Aleutian Islands in Alaska, showing the historical areas of rupture from shallow earthquakes from 1930 to 1979. And you can see these are the little kind of these globs represent where most of the earthquake activity has occurred, and then there are these gaps, and they're just saying basically that the next earthquakes are most likely going to occur in these gap regions. They have a high probability of having an earthquake because most likely they're on a tectonic boundary here where there's a fault within these areas. So they occurred here. There's another gap here and a gap. So so that's just kind of interesting there. So here's some important facts from earthquakes. 1906, San Francisco killed 500. The first revealed the importance of faults. In 1923, Tokyo killed 140,000 in firestorm. In 1964, there was an earthquake that killed about 200. It wrecked Anchorage, Alaska, and there was a tsunami on the west coast. And then in 76, in China, there was a urban area that was an area of 10 million people, killed 240,000. So that was the deadliest in the 20th century. So we've got a lot of earthquakes, historical earthquakes, some really bad ones. So here's California. San Francisco is doomed. The great earthquake, death and destruction sweep the Bay cities. Hundreds die in ruins. So that's kind of in the paper, and that was, I think, in the 1900s here. I can't read the date, but 1900. So what you guys are going to do for your laboratory with Jocelyn is you guys are going to actually locate the epicenter of an earthquake. So remember, I kind of talked about you'll have your you're going to have on your x-axis, and then on your x-axis and your y-axis, you're going to have distance on your x, and then on your y you'll have your seismic waves. And remember, you basically are going to take a compass. You'll take a compass like this. Let me grab one here. I've got a compass. So you're going to have a compass like this. You'll use this to basically draw 3 circles. You'll draw the diameter of 3 circles, and where those 3 circles meet is going to be the epicenter of the earthquake. And you'll determine that from your PNS waves. So here's one circle that was in Rio de Janeiro, where I've swam in their oceans because my wife's from Brazil. And then this is the other wave that's the red one is from Berkeley, California. So there's a seismic station there, as well as in Rio de Janeiro, as well on the East Coast. So you're going to triangulate that just like a GPS triangulates from the satellites that are orbiting our Earth. You can triangulate your location anywhere at any time, even in your cell phone. If you get lost, you know that as well. So the epicenter would be this right here. That's where it would be. So that's all I have for this afternoon. I hope all these lectures kind of help. Maybe you guys are reading your book while I'm talking, which is good. If you have questions, send them via email, or through Canvas. You can do that as well. We'll be getting into, on Wednesday, geologic structures. We'll be talking about big, huge basins and domes, and looking at how rocks behave under stress. So this should be pretty exciting. So thanks again, and I'll talk to you guys soon.